In this video, we'll be solving this question. The question says, where in this figure could you place a proton so that the net force acting on it is 0? And we're informed that the magnitude of the positive charge is 4 times that of the negative charge, and we should explain our result. This is what we have, and this is our positive charge. That is 4 times, this is plus 4q, and we have minus q over here, which is the charge. Then, and we're asked to find at what point or where will we place a positive charge, that because a proton is a positive charge. So where should we place a proton in this? So in such a way that the net force acting on this will be neutral, will be electrically neutral. So there are 3 places where we can place, or we might place, the positive charge. But the problem is that the place where we place the positive charge, will the net force be 0 at that point? So we can consider the first place to be this as 1. Okay, let me change the color of my biro. We have here to be 1, which is we have here to be 2, and probably somewhere here to be 3. This region, then this region, and this region. So if we consider the first part, the first region, if we decide to place a proton somewhere here, maybe let's place a proton here, what happened? Will the net force be 0 along this? The answer is no. The reason is that you have a negative charge over here, and you have 4 positive charges in this position. So these 4 positive charges, we already know that the like poles repel and unlike poles attract. So this will be attracting. The negative charge will always be feeling force from this end, even though we placed a positive charge here. So, and since we placed a positive charge here, it will be repelling. So in this case, the positive charge over here doesn't really make it to be like the net force here to be 0 yet. So there is actually the force going towards this side. That means the greater force is moving towards here, and the force in the total system cannot be in equilibrium. So in that case, this will not work. Placing a positive charge or a proton in this region will not work. So let's consider another one. So at this point, we have that this point cannot work. That's region 1 cannot work. There's no way we can place it over here and we get the whole charges to be in equilibrium. So the second point is this. What if we decide to place a proton somewhere here? What will happen? If we decide to place a proton here, a lot happens. There's already existing forces within this before we decide to place a positive charge. So, and the positive charge here is 4 times that of the proton, right? And that means we are having like about 5 positive charges acting on this. Then in this case, the system cannot be in equilibrium. Like the forces acting on this cannot be in equilibrium. So in this case, we can say the region 2 as well cannot work. So if the region 2 cannot work, then we are left with one region. So this is region 3. Now, the truth is that if we have a if we have a proton in this region, let's say somewhere here, then we have 4 charges acting on this, right? And we have a proton as well trying to act on this. But the problem is that there are greater forces coming from here, coming from this 4q acting on this negative q over here. So, and there is tendency that the influence of this force will be felt within this region. Within this region, there is tendency that the influence will be felt within the region, right? So, and if the influence is felt within the region, then it will affect the position in which we will place the charge, right? If it's too closer to this negative q, then we have that the net force cannot be 0, because the charge from here will be affecting the proton placed within the region. If it's too far away from this positive charge, the negative charge, then we can see that the impact of this will not be felt at all outside. So in that case, we still maintain the original structure, which is this plus 4q and minus 4q. So the stuff is that it can be too close to minus q, and it can't be too far away from minus q. So at this point, how do we really determine where to place the positive charge? We've understood that this region will work. Yeah, the region will work, but we can't really tell at what point should we place the positive charge. So how the question is, this region works, all right, but the question is how or where should we place it? It's a big question. So for us to do it, let me erase this, and let me erase this as well. Okay, then we have that from the laws of electrostatics, we have F, the force acting on the charge, to be equal to kq1 q2 over r squared. Good. So we are going to make use of this formula to determine at the exact point where to place the positive charge, which is the proton. So let's assume the distance from here to this point is d, right? And the distance, let me change the color of the pen as well. Can this work? Good. And the distance from this point to somewhere where the charge will be in equilibrium, let's assume it, we don't know, but from here to, okay, let me not let me not use this to say, okay, let me use arrow to indicate that we don't know at exact points where it's heading to or where it will be. So let's assume it to be x. Good. So with this, I can say that using this formula, I already know that the charges between this and somewhere we will place the proton where it will be in equilibrium will be this. So the force acting on it will be F is equal to Q and E divided by KQE divided by x squared. But the charge here should be Q, 4Q rather, or 4Q. This should be 4Q. Okay, now if I call here, let me label this S. Good. Let me label here S. And the other part will be the distance from this charge. Down to somewhere we don't know. Wherever we'll place the positive charge or the proton. Let's call this D. Right. This F1, then F2 will be equal to, oh shit, I missed Q here. There should be Q in F1. Yeah. So this is Q, right? And QE divided by, now we have X plus D all squared. This should be minus S. This your X minus S, because since the distance from this to the equilibrium position is X, and the distance from this point to this point is S, and distance from the point to the equilibrium point is D. So for us to find D will be equal to X minus S. That's the distance of this. So, and for the whole system to be in equilibrium, we have that FQ, that is the positive force, F positive must be equal to F negative. So at this point we can equate these forces, that is F1 is equal to F2. Then if we said F1 is equal to F2, then we can have this to be 4Q K4QE divided by x squared is equal to KQE divided by x minus s squared. So we can cancel out this, cancel Q as well, E and E. So we have this to be 4 divided by x squared is equal to 1 divided by x minus s all squared. We can take the square root of both sides and we'll be having 2 divided by x is equal to 1 divided by x minus s. So making x the subject formula, this is, first of all, cross multiply. We have 2x minus s is equal to x. So this is 2x minus 2s is equal to x. So this can cross the sign of equality and we'll be having 2x minus x is equal to 2s. So x is equal to 2s. Now we've gotten the total distance, right? 2s. So let's go back to the diagram. So at this point, let me change the color of the pen, or let me go with blue. Okay, we've gotten the distance from this to be 2s, that is x is 2s, and we already know that s is distance from here, this point to this point. And as well, we have that D, which is the distance from this negative charge to where we are going to place the positive charge, that is the proton, is x minus s. So we can now say that D will be equal to x is 2s minus s. This will be s. So that means it has to be the distance from here to here. That's what we'll have over there. So, and the distance, okay, let's count 1, 2, and 3, right? So from this point, it can as well be 1, 2, and 3. So we are going to place the positive charge or the proton in this position, plus E. Thank you for watching this video. And if you have any question, feel free to reach out to us. You can as well comment, like, and share with your friends, and kindly subscribe to this channel. Thank you.